Good morning. I'm Scott Coblitz.
And I'm Paul White.
We're both going into our junior year and have spent our summer undergraduate research in engineering under Professor Michael Bernitsis of the Naval Architecture and Marine Engineering Department. Our research concerns the vortex-induced vibrations aquatic clean energy converter, also known as Vivace.
Vivace is needed to provide an alternative to the current energy methods we are using here on Earth. As of recently, petroleum, coal, and natural gas remain the leading energy sources worldwide. Next in line are nuclear and hydroelectric energy. Instead of depleting our natural resources, Vivace attempts to harness the hydrokinetic energy through one of the largest sources of clean renewable energy. This source is the marine environment, and it absorbs 285 zetajoules of solar energy per year.
Vivace is a hydrokinetic energy converter that utilizes the hydrodynamic phenomenon of vortex-induced vibrations to harness the power of a current. This image shows the process of alternate vortex shedding around a bluff body. This alternation is responsible for the oscillation of the cylinder. Power is then extracted from the oscillation. Here is a video of the Vivace system being run in the lab. Because this phenomenon occurs at low flow speeds as well as high, the Vivace system has the potential to be used in many locations, more so than other marine renewable energy devices. Another positive aspect of the Vivace system is the high degree of scalability. This scalability led us to our first task.
Our first task this summer was integrating 3D modeling with a full system analysis. We strived to create various 3D CAD templates based on 6 different geometries of Vivace modules. These geometries were predetermined based on hydrodynamic considerations. We then considered different arrangements of modules to form an array. We drew the templates in Unigraphics NX5, which was our program of choice, and then proceeded to write macro files to allow for easy scaling of the modules. Our macro file allows a user who might be inexperienced with a particular CAD software to simply reply to a prompt that is given when the file is opened. In our case, we allowed the user to scale the Vivace module using as little effort as simply entering the diameter of the cylinder that they wish to use.
To supplement the visuals offered by our CAD, we ran a system analysis for varying water flow speeds, varying cylinder diameters, and varying cylinder configurations. This helped us to determine which Vivace configuration has the greatest power density, and also how many modules of a certain geometry are needed to produce a targeted amount of power. This slide compares the power density of the Vivace system to those of various other marine renewables.
Our next objective over the course of this summer was to develop a quick design for an interested large corporation. We were given size constraints as well as a minimum Reynolds number that our design must satisfy. After CADing up and analyzing our system, our proposed design, we found several better ways to utilize the build space, and ultimately that led to generating more power in the same amount of space.
Our current project is also a system optimization. We were given a range of flow speeds as well as a range of cylinder diameters and a desired power output. Given only these few constraints, we found that we had a vast number of designs to choose from. To assist our system optimization, we divided the flow speeds into 2 different regimes. From there, we analyzed several different aspect ratios for each cylinder configuration. At each configuration, we've taken power, power density, and dimension calculations for each flow speed and diameter. After calculating all of these quantities, using various criteria, we will determine the best Vivace system for the given flow regime and range of power outputs. We are still analyzing our results to determine the best system setups.
Through our research this summer, we learned and improved our CAD skills with Unigraphics NX5. We also learned how important teamwork and communication skills were with two people working towards the same goal. It was also neat to learn that research has real-world applications. For example, Vivace has caught the interest of our government and several large corporations. They're currently working with Vivace. It is also cool to learn that in 2010, Vivace will be powering a new river wharf on the Detroit River.
In closing, we'd like to thank Professor Bernitzis as well as the SURE program for the excellent opportunity this summer. We'd also like to take this time to highly recommend this opportunity to anyone who has the chance to participate in the SURE program or any other undergraduate research. Thank you for your time.
Thanks.